Hi everyone, I'm the CEO and founder of X-Trace, and today I'm going to present like what we're building for private agent memory. Yeah, so I think already like throughout the whole event today, we already know like how important like private context is. So you just have to know that every time when you're searching through like a unencrypted vector database, you're exposing your query, and then you're like storing your memory. Like it will also show like all the preference, decisions, and all the institutional context you have. And then also like all the agent trajectory that is stored inside. So basically my philosophy is that you should own the context and rent the intelligence. So making it private is really the only way to efficiently like own the context. So this is kind of just how like we are different from all the other vector DBs. Like from the server view, like other vector DBs, you can see your queries, your trajectories, your memory, any thoughts you store inside. In X-Trace, it's just all ciphertext. So how does it work? So we're kind of at first we're also really trying to solve this problem. We kind of look at to a lot of like research like crypto and all that. Most of them are like fully homomorphic encryption based, which means that to calculate like the semantic distance between like two embeddings, like for just like a 1024 vector, you have to do 1024 embedding operations, like FHE operations, which is like really expensive. And what we're doing is that we discovered that you actually have a way to just do one ciphertext operation to calculate the difference between two vectors. And the key realization is that if you transform embedding from floating point to binary, it's actually distance preserving. And then you only care about this right now when you're doing semantic search. That's all you care about is distance. And then we can do like a additive homomorphic encryption, which is like a partially homomorphic encryption, which can be a lot faster, almost like 1,000 times faster. You just need to do one partially homomorphic encryption operation versus like 1,024 or like X amount of like FHE operations per vector. So that's kind of how we do it. So the way it works is that on your machine, the embedding is encrypted with like your binary vector and then the AES encryption and then AES encrypted. So everything will be our X-Ray server all encrypted. And then when you submit an encrypted query to our system, we'll do like the additive homomorphic encryption in the server and return you the data. So for you to decrypt and only you can see it. Yeah, so this kind of created a lot of interesting use. Oh, sorry. Oh, sorry, we're storing it in pager encryption. So we encrypted the binary vector, and we realized that you can just do one additive homomorphic operation to calculate the distance between two binary vectors. Yeah, here is this. So so we're not still storing the vector in plain text. Yeah. So we can still do semantic search on ciphertext and making sure everything's encrypted. Yeah. So this unlocks a lot of like interesting use cases. Like we already built out like our own cloud plugin that essentially you can encrypt all your data. And then all of this will be hosted on our X-Ray server. And then you can share key so your colleague, your other agents, or anyone can like access this data and make sure only they have access to it. Because only the secret key holder will be able to access the data, and X-Trace who hosts all your data for you, we have a cryptography guarantee that we never see your data. Yeah, so this is basically how we design like the encryption system. And we also have like our own design on the memory system. So when you think about memory, there's really two kinds of memory. And then like I can argue like pre-2026, most of the memory are about semantic memory. So at that time, the problem is like there's limited context window. So what is the best way to like fit all the context I have into the memory, like the agent's context? And most of the benchmark or the research like local mode, low mem EV and all that are benchmarking against like user and agent chat. But that's not the case in 2026 anymore. Like agents are doing a lot of tool calls. They are doing tons of agents. They have their chain of thoughts. They'll retry and have a lot of agentic trajectory and rollouts. So that's where procedural memory comes into play, which is like how does agent accomplish tasks? So actually it's capturing both the semantic and procedural memory. So like the semantic memory we built is based on how we call belief revision system. It's actually a mathematical paper that talks about how philosophy works when like an agent learns about belief and how they update the world about belief. It's like some epistemology thing. So we can make sure like all the semantic memory stored in your system are mostly up to date. We have a resolving mechanism and make sure like not everything has record and version. And then the procedural memory is how we distill and get like agentic trajectories. So one key realization that we find out is that if you just directly use semantic search on procedural memory, it usually will not work. Because like real user will just say, help me debug this, help me deploy this. So what really work? So how H3 does it is that we anchor like the tokens of the agent as trigger conditions. So when it's calling a certain, editing certain files or doing certain triggers, you basically break down like the chain of thought of the agent and make sure like we can inject context insight and steer it pre-token. So when it's just decided to call a token, like say I just want to remove my database for some unknown reason, like the agent is doing something weird, we can stop it and then inject the context insight that like, we're completely every rules and never do it. And you can, that's how you kind of make sure that consumer memory will be fully executed. Say one like ignore guardrails and all that. And on top of that, because of share is still like certain lessons learned that has like failed retry loops and all that. Happy to go deeper inside because it's kind of late. Yeah, so basically that's kind of what X3 is building. So we actually have like our vector database encrypted vector database out that people can directly get API and try it out, and it's open source, so you can verify the encryption schema locally. So I think the docs is here. And the product is kind of like the memory hub that we're building that allows different teammates to share their agent brain, share their context. So everyone can have like a holistic view of everything. But because this product is like more consumer facing and we don't have we have a UI for it. So this one we have like, it's not encrypted, but the actual vector database are all encrypted. Yeah, thank you so much. Any questions?
So the server side, we still think do a linear scan, or does it really scale the size, like linearly the size of the database?
Yeah. So currently you have to do like the linear scan of the whole database, but we can, because we're using binary embeddings, so we can use like inverted file index. So essentially we can have a square root of like the whole like search. So you don't have to search through everything. You can still have like an encrypted index for it.
But I'm just not very familiar with this.
Okay, yeah.
How is it?
Yeah, so you can think about like the most naive way is that we can group like all this binary vector into bit buckets. So you can think about like they all have like certain like index. Like for instance, let's do the most naive one. It's like those 4 bits are always the same for like 20 vectors, right? But on the client side, they know like which range of vector to search. They can just search on like a part of that. So that's kind of how we combat with like instead of just like linear scan, we can do like square root. Yeah.
My question wasn't very similarly actually. It's like in traditional vector-based systems, binary vectors are really nice. You can excellent hop path them super fast.
Yes.
For dots. And so I was just curious if like there was some equivalent to that in your like encryption image.
Yeah. So basically, like that's kind of how I get the vector similarity distance instead of like, because if you do like a cosine similarity, you have to kind of just do like 1024 operations if you have like 1024 like entries in your vectors. And using this system, you can basically just do one addition operation between 2 binary vector in some like specific way. Then you can just directly get a distance. They have
Like,
distance.
I think I'm talking more about box 5. Maybe I'm misunderstanding, but it's like after the vector's been encrypted, is there still like inefficient errors? That sounds like your answer is there is in some encrypted file.
Yeah.
Okay. But that's like okay. So you are losing a little bit, right? It's like the IVF is going to be slower than extra plot file, but that's okay because it's private.
Yeah, so we do. Yeah, it'll be slower compared to vector database for sure, but this is kind of like the best way we can get to say around like 10,000 chunk in less than 1 second end to end. Yeah, without any like specific index like linear scan. So you add like a specific square root on the index, you can say it's like 1 million in 1 second. Yeah.
I've got one more question. So actually bringing back to the Kai's talk, did you see that question?
Yeah, I'm not sure. Yes.
Well, okay, so I was talking about this one thing about precision versus recall. So whether search returns, I know I'm butchering this, you're judged on how accurate the thing returns is versus that's precision, and recall is whether it gave as many relevant documents as possible. Is that right on precision versus recall?
Yeah, what percentage of
Excited with my
Yes.
Mhm.
Okay, cool. So I was wondering, have you analyzed your system through that like lab?
Oh, yeah. So that really depends more on like the embedding model you're using and how you embed. Like if you embed like a really long context or like didn't break it, chunk it correctly, that'll be the problem. Like, so we're kind of just doing like a distance preserving encryption method to make sure like we can still do operation on top. So that's not like what we really do in this part. But on the memory part, we do have like specific ways to make sure like the recall and precision is like pretty high, based on like we have like a small language model, context selector, and all that, and have to do dive deeper later. Yeah.